Welcome again. Uh, I couldn't explain something in the last video, so I'm going to explain it now. I have to establish a clear-cut relation between simple harmonic motion and circular motion. So I'm drawing a kind of circle here, and you can see here that there is a circle and it's completed now. And suppose that the radius of this circle is a, and some object is moving with constant speed v naught or something, and its angular velocity is omega, and the speed is constant, or b naught omega, everything is constant, so that and it has made some angle. It was initially somewhere here, and its angle was with x-axis. Its angle was phi naught, and it is now here after time t. So this angle must be equal to omega t. Its x coordinate. Its x coordinate can be found from this value. And so that its x coordinate, you can write here a cos omega t plus phi naught, and its x coordinate is here. And if you differentiate it once, that is dx by dt, the value you will get is omega a minus sine omega t plus phi naught. And if you differentiate it again with respect to time, you will get minus omega square a cos omega t plus phi naught. And x is of course a cos omega t plus phi naught. So you can write the whole thing as x, and you will get your equation simply as d2x by dt square equals minus omega square x. And or you can write it like this: d2x by dt square equals plus omega square x equal to 0. And this is the normal equation, differential equation of simple harmonic motion, because this is called the simple harmonic motion, or this is called the simple harmonic motion. So this is called the simple harmonic motion. So I think I would be brief, because I don't describe here the detailed motion or detailed theories, because I have my own limitations here. This is, I think, you can find there is a relation between simple harmonic motion and the uniform circular motion. And this is the differential equation of simple harmonic motion, because this is written in differential in terms of derivatives. Though this is the basic simple harmonic motion, sinusoidal motion equation, so this is, and so this is, and this equation is written in terms of differential equation here. I can understand these things. And I'm going to remove it, because I don't need to talk about it anymore. There is a problem called the heading of the problem says there are no oscillations. Of course, in this problem there will be no oscillation like oscillation, but the equation of oscillation exists. वो oscillation का जो इक्वेशन है वो आएगा इसमें. कुछ इस किस्म के भी प्रॉब्लम्स होते हैं. Read the statement of the problem. It's just a start, so I'm trying to get started. And the problem is a long train moving by inertia. That means its engine is closed, shut down, and it is moving simply by inertia. It will have some velocity and it will slow down eventually. So a long train moving by inertia enters a slope of angle alpha. You can see in the picture. When the train has completely stopped, half of its length is on the slope. How much time has elapsed from the start of the climb? That means जब से ये इसने climb करना शुरू किया on the incline. How much time has started from the start of the climb to the stop? And the length of the train is L. And there is no slipping anywhere. That means the wheels of the train was rolling, purely rolling. That means you are free to use the mechanical energy conservation. And let's use the law of conservation of energy. And let's say that a part of the train of length x, say length x. This is not the whole part. This is basically the length x. The length x has entered the hill. मतलब वो hill पर सिर्फ x length of the train has entered the hill. Then we can write a conservation of mechanical energy equation here. Suppose that the initial kinetic energy or initial speed of the train after then its engine was shut down was V0. At the moment when the train started to climb the hill, its velocity was V0 initially, and its total mass is m. And so it has and datum I would like to take here, so that potential energy here is equal to 0. So it has only kinetic energy at the start of motion, at the moment when it started to climb the hill. So its initial kinetic energy I can write here half mv naught square. And now its speed is something else. It has slowed down. Its speed is v. Simply not v naught. Its speed is v. So its kinetic energy can be written as half mv square. This is all of the train is moving with the speed v. So I wrote down its kinetic energy by simply half mv square. And its potential energy. Its potential energy is because some part of it, a length x of the train has entered the hill, has reached the hill. So the length of x part, the mass of x part, I would like to write its gravitational potential energy. So I'm going to write down its mass, and its mass I'm going to write mx upon L, and g mg, and the length it's reached is x by 2 sine alpha, because it's long and its center of mass is at the midpoint of the part of the length x. So this length is going to be x by 2 sine alpha simply. This is a perpendicular, so the height reached by it can be written as x by 2 sine alpha. So this is the potential energy of it. And we know that its velocity right now, its velocity is simply dx by dt. And now I would like to differentiate the equation obtained with respect to time. And if I differentiate it, it's the left hand side of the differentiation becomes 0, because it is not changing anymore, and v is changing. So I can write here m half m 2b dv upon dt and plus mg upon L, and again there is a half here, and sine alpha, all constants, and x squared, that is 2x dx by dt. And I get something like 0 equals mv dv upon dt plus mg sine alpha upon L x dx upon dt, and v equals, since v equals dx upon dt, so I can cancel it as well, so that my equation, and m gets cancelled out as well, so my equation becomes dv by dt plus g sine alpha upon L multiplied by x equal to 0, and dv by dt is of course d2x upon dt square, or plus g sine alpha by L into x equals 0. And this equation comes, and this equation reminds me of a simple harmonic motion, because its equation, the equation of SHM can be written as well, d2x upon dt square plus omega square x equals 0. And that means if I can compare both these equations, I can get my omega, and that is equal to under root g sine alpha upon L. And if angular velocity is t, angular velocity is omega, then its time period is simply 2 pi by omega. Time taken to complete one circle is angular displacement, that is 2 pi by omega. And what was the problem? Problem was simply how much time has elapsed from the start of the climb to the stop. Motion started from here. When it tries to climb the hill, the train tries to climb the hill, but it gets stops at this moment. And when it stopped, when the train has completely stopped, half of its length is on the slope, half. That means it has completed 1/4 of the simple harmonic motion only. So your answer is simply t by 4, and that will be your answer. Thank you very much for watching.